In the previous video, we introduced the objectives for this series on general chemistry. Today, we begin our discussion of atoms. Earlier, we defined atoms as the tiny particles that comprise all matter. We then defined matter as anything that has both mass and volume. Because our earlier definition wasn't very specific, we need to elaborate on it a little bit more in order to have a better understanding of the overall scope of the scientific study of chemistry. So, what exactly are mass and volume? Mass essentially is a measure of how much stuff an object is made up of, and its unit is the kilogram, or kg. Volume, on the other hand, measures how much physical space an object takes up, and it is most commonly measured in cubic meters. To reiterate another point from the previous installment, chemistry can be simply defined as the study of matter, or more specifically, as the study of the properties and applications of the substances that make up our material universe. So now we get to a very fundamental question. We've already established that mass is a measure of how much stuff an object is made up of. But what exactly is the stuff that all matter is made up of? Simply put, all matter is made up of tiny particles called atoms. To give an idea of exactly how small atoms are, we can estimate that a single human hair is just about 1 million carbon atoms wide. Not 1 million carbon atoms long, but 1 million carbon atoms wide. This means that most of the ordinary objects a person might encounter in everyday life, like a table or a chair, will be made up of trillions upon trillions of atoms. As amazing as this is, we can go even smaller in our study of matter's composition. We do this by asking the question, if all matter is made up of atoms, what exactly are atoms made of? Answering this question involves traveling to the subatomic level, looking at the three types of particles that atoms themselves are comprised of. These particles are called protons, neutrons, and electrons. We differentiate between these three particles by looking at the electrical charge attached to each. A proton will always have a positive charge, an electron will always have a negative charge, and a neutron is always devoid of any electrical charge, making it electrically neutral. Just to reiterate something here, because protons, electrons, and neutrons are all subatomic particles, they are all smaller than individual atoms. So if a single human hair is 1 million carbon atoms wide, imagine how many protons or electrons might be needed to build one hair on a person's head. Now, here we have a rather crudely drawn diagram of a carbon atom. It might be noticed that the atom is drawn as being made up of these tiny spheres. The protons are the white-colored spheres, the neutrons are colored in blue, and the electrons are in red. Of course, protons, neutrons, and electrons in the real world aren't actually red, white, and blue, so the coloration here is only for illustrative purposes. Moving past that, it might also be noticed that the protons and neutrons are clustered together in the middle of the atom. This cluster of protons and neutrons is referred to as the nucleus of the atom. The electrons here are essentially orbiting around the nucleus in a similar way to the motion of the planets around our sun. Each planet, whether Venus or Earth or Neptune, follows a specific orbital path. Electrons behave in the same way. They move on fixed paths as they rotate around the nucleus. We will discuss the exact configurations of electron orbitals in a future video. All the three subatomic particles discussed so far are important in chemistry, but the particle of interest in this video is the proton. The reason for this is because the number of protons a particular atom possesses is what determines the atom's chemical identity, which in this context can also be referred to as its chemical element. There are currently 118 known elements, which in turn means that there are 118 types of atoms known to exist. The amazing implication of this is that every single substance in the universe can ultimately be broken down into these 118 elements. Even if we restrict our discussion to the substances that make up living things, the substances that a biochemist might be looking at, for example, we will see that all the proteins, all the growth factors, all the different macromolecules that are the building blocks of life, all of these are nothing more than mixtures or compounds of one or more of these 118 elements. The more immediate implication of this is that the simplest chemical element, hydrogen, has exactly one proton, whereas the atoms of the largest, or oganesson, have 118 protons. Other elements have a number of protons somewhere in between 1 and 118. Just a few examples are given here. Carbon atoms always have 6 protons. oxygen atoms will always have 8 protons, and gold atoms will always have 79 protons. For easy reference, all the 118 known chemical elements are tabulated in a table called the periodic table of the elements. The first person to make something resembling the modern periodic table was the Russian chemist Dmitry Mendeleev during the 19th century. His original periodic table only had 28 elements listed on it, but more were added as they were discovered and isolated. A typical periodic table is drawn with many little squares on it, almost like an enormous quilt in a way, and each of these squares is devoted to the presentation of a single element. Here we have an example of a square on a typical periodic table. There are essentially 4 pieces of useful information we can derive from this square. The first is the name of the element, which in this case is sodium. So this is the periodic table square for sodium. Next we have the letters Na, which represent the element symbol for sodium. Element symbols are basically a shorthand way of referring to elements, so chemists don't have to write out the word sodium every time. It might also be apparent that the letters Na don't appear in the English word sodium, which goes to illustrate that not all element symbols are directly derived from the English language names for the elements involved. In this case, the letters Na are used to represent sodium because the Latin word for sodium, natrium, includes those 2 letters. Thirdly, we have the number 11 written on the top left corner of the square. The number 11 represents sodium's atomic number, which is the technical name denoting the number of protons found in a single sodium atom. Finally, we have this decimal number, 22.990. This number is called the atomic weight, and it is here to denote the approximate mass of a single atom of that element, in this case sodium. We will discuss atomic weight in greater detail in a future video, so the only thing to note down at the moment is that different elements have different atomic weights, and that generally a larger element, or one that has a higher atomic number, will have a higher atomic weight to go with it. At this point, we've discussed atoms themselves in some detail, but as with any scientific concept, it's also worth knowing exactly how atoms were discovered. This is especially pertinent here, because atoms themselves are far too small to observe with the human eye, or even through the most powerful microscopes. So, how exactly did we come to know that the universe is comprised of atoms? The story here begins with the Greek philosopher Democritus, who is the first to hypothesize that all things might be made up of tiny particles. He named these tiny particles atomos, which comes from the Greek word best translated as indivisible. Again, he was trying to hypothesize on the smallest unit of matter, which explains why he would assign these tiny particles their name. Chemistry as a whole was dominated for many centuries by the ideas of Aristotle, another Greek philosopher who believed that everything was made up of 4 distinct elements: fire, water, earth, and air. Many years later, the English chemist John Dalton would challenge the prevailing views of his time when he wrote about his own atomic theory in the early 1800s. There are several points involved in Dalton's atomic theory, so we're just going to summarize them briefly here. The first point is that Dalton believed all matter is made up of atoms, or tiny particles. Secondly, Dalton hypothesized that elements were chemically unique. In other words, an element couldn't be broken down any further. An element, then, was basically a box that specific atoms could be stored in, and all atoms of any particular element would share characteristics. This, of course, would imply that atoms of one element would have different properties than atoms of another element. So for instance, carbon atoms and gold atoms belong to different element classifications, and therefore they will behave differently when exposed to the same external conditions. The fourth of Dalton's points is that there are substances called compounds, and according to his theory, compounds are unique combinations of different atoms from 2 or more elements. In addition to this, he also believed that any given compound will always be made up of a fixed ratio of different atoms. One common example is carbon dioxide gas. Carbon dioxide, or CO2, will always be made up of 1 carbon atom and 2 oxygen atoms fused together. Dalton's fifth and final point states that atoms themselves are never created nor destroyed. Rather, they will only bond with different atoms to make new compounds whenever a chemical reaction occurs. Chemical reactions will be a major focus of the following video, as well as almost all of Unit 3. But for now, we can illustrate the basic concept of a chemical reaction by looking at rust. If a person leaves a box of iron nails, or anything made of iron really, out in the rain, the iron in the nails will fuse with the oxygen from the rainwater to form rust. As a quick aside, the chemical name for rust is actually iron oxide, and it might be noticed that the term oxide comes from the same root word as the word oxygen, implying that iron oxide or rust is essentially a mixture or compound of iron and oxygen. When rust forms, neither the iron atoms nor the oxygen atoms disappear. All that's happening is that the arrangement of the atoms is changing. They are breaking away from their current compounds to make new ones. For those who are familiar with physics, the law of the conservation of mass, the idea that matter is neither created nor destroyed but only changes form, is closely connected to this idea of the conservation of atoms. Because all matter is made up of atoms, if we can say that atoms are neither created nor destroyed but only change form, we can also conclude that matter is neither created nor destroyed but only changes form. It is important to reiterate that much of modern chemistry was established on the foundation of Dalton's atomic theory, and so it is quite important to remember these 5 central points. Interestingly enough, the main proof for the existence of atoms comes from experiments that were actually meant to verify the existence of subatomic particles. There were 3 chemists who were involved in providing evidence for the existence of subatomic particles: J.J. Thomson, Ernest Rutherford, and James Chadwick. Each of these men conducted different experiments, but it isn't really necessary to know the details of these experiments specifically. What is important is knowing exactly what each of them proved. Let's begin with J.J. Thomson. His experiments proved the existence of the electron, the negatively charged subatomic particle. Ernest Rutherford gave evidence for the existence of the proton, the positively charged subatomic particle. Besides that, he also gave evidence for the currently accepted model of atomic structure, the idea that an atom is composed of a nucleus with electrons orbiting around it. Last but not least, James Chadwick was instrumental in proving the existence of the neutron, this one subatomic particle that does not have any electrical charge. We close out this video by introducing 3 practice problems. We begin with example 1. Look at a periodic table. What element is represented by the symbol AS? If you like, feel free to pause this video while you think about this one. The answer to this question, of course, is arsenic. Arsenic has an atomic number of 33 and was widely used as a poison throughout much of human history. Modern applications of elemental arsenic include pesticide and semiconductor manufacturing. Moving on to example 2. What exactly did J.J. Thomson's experiments prove? J.J. Thomson's experiments proved, or to put it more accurately, provided evidence for the existence of the electron. One final question. What determines an atom's chemical identity? The thing that determines an atom's chemical identity is, of course, the number of protons that it possesses, which is also referred to as its atomic number. Just to give a quick example here, if an oxygen atom, which has 8 protons, somehow managed to lose one of its protons, it would stop being an oxygen atom and would instead become an atom of nitrogen, because nitrogen has an atomic number of 7 on the periodic table. In the next video, Unit 1, Video 2, we will be taking a closer look at molecules. Thank you for watching.